Hello and welcome back to Dr. Logic Awkwardly Does Logic. I introduced you to System S4 last time, and this time we're going to dive deeper into it. And in particular, we're going to look at the question of iterated modalities. Because remember, the whole point of us looking at systems stronger than T was that we wanted to find ways of reducing complex modalities into simpler ones, because we might not have any intuitions about whether something that is necessarily, possibly necessary, possibly necessary implies that it's necessary. We might be able to have some intuitions about whether something that's possible is necessarily possible, or necessarily necessary is necessary. Simpler things like that. So we're just going to dive right in. And what I'm going to do is I'm going to show you the reduction principles that we can prove in S4, and then we'll go about actually proving them and showing this. So recall that S4 is system T plus the 4 axiom, which is necessary P implies necessary P. So that's what we're working from. The 4 modal reduction principles that we get in S4 are the following: that necessary P is equivalent to necessary P, that possibly P is equivalent to possibly P, that necessarily possibly P is equivalent to necessarily possibly P, and our last one is that possibly necessarily P is equivalent to possibly necessary P. Now, what I mean by is equivalent to, is a modal reduction principle, this is all just, this is all because these are going to be theorems of S4. So they are principles that we can prove using the K axiom, the T axiom, and the 4 axiom. So let's go through and see how this goes. I'm going to start with this one because this one is very easy. First of all, we have that necessary P implies necessarily P. This is one of our axioms, i.e., it's the 4 axiom. We also have that necessary P implies P. This is the T axiom. Now, we can take a substitution instance of this to get the converse of our first theorem. That is, we can swap P for necessary P, and then what we get is that necessary P implies necessary P. So this was uniform substitution, putting in box P for P on line 2. And then propositional logic says if you've got that P implies Q and Q implies P, then, essentially just by definition of notation, you can stitch the two together to get that necessary P is equivalent to necessary P. So that's just propositional logic on lines 1 and 3. And okay, I wrote the equivalence down opposite than I did in the statement up here. So just to remind you that in propositional logic, you can flip biconditionals back and forth. So there you have it. Now, once we have proven this first one, proving the second one, i.e. the diamond analog of it, is very easy. I'm not going to give you a proof of that, but I will give you the hint. So it's going to be from the fact that we have already proven this principle, plus uniform substitution. You're going to want to substitute in not P for P, then use contraposition and modal interchange. So from that should be all that you need to prove the second modal reduction principle on your own. So let's take a look at the more complex one, this one here. Here we've got more steps that we need to go through, unsurprisingly, given that this is a more complex biconditional that we want to prove. But it's going to start off by using theorems and axioms that we've already proven. So remember that since we've got in S4, we've got the T axiom, which is necessary P implies P. We also have theorem T1, which is that P implies possibly P. So I'm just going to start right away with a substitution instance of T1 rather than writing it down and then taking the substitution instance. And the substitution instance is I'm going to replace P with necessarily possibly P. So necessarily possibly P implies possibly necessarily possibly P. And this is uniform substitution on theorem T1 with necessarily possibly P substituted in for P. Now I'm going to move my proof over here a little bit more so I've got more space. Now, once we have this, we also have all of the rules that we've used in our previous system. So all of the derived rules in K, we still have in S4. So I'm going to use derived rule 1 and stick boxes on both the antecedent and the consequent. And the reason that I'm doing this is take a look at what we've got here. So let's see, this is derived rule 1 applied to line 1. On the consequent, I now have part of what I am trying to prove. Now, what I have in the antecedent doesn't match. However, given that we have just proven that necessarily P is equivalent to necessarily P, I can reduce these two boxes to a single box using substitution of equivalences. So this means that necessarily possibly P implies necessarily possibly P. So again, this was through substitution of equivalences on line 2 using the fact that we've already proven, namely this equivalence. And this is half of what we want to prove. It gets us from the left to the right. It's a biconditional, so now we need to go the other way around. And it's going to be a very similar sort of proof. First, instead of taking a substitution instance of T1, I'm going to take a substitution instance of T, namely that necessarily possibly P implies possibly P. So this is uniform substitution on the T axiom, where I'm just replacing P with possibly P. Now, we have another derived rule that says, just as derived rule 1 says you can stick boxes on both of them, derived rule 3 says you can stick diamonds on both of them. So this means we get diamond, box, diamond, P implies diamond, diamond, P. So that's just using derived rule 3 on line 4. Now, okay, I hadn't proved this one, but I left that as an exercise to you. So I'm just going to take it as given that you've given me this proof, because now I can do that same reduction over on the consequent side. So the antecedent stays the same, but I'm going to reduce those two diamonds back down to 1. And so this is, again, substitution of equivalences on line 5 using modal reduction principle 2. And now we're getting very close, but start thinking in terms of strategies. So we have kind of put a bunch of modal operators on, reduced some of the duplications, but now we still need to add more modal operators because we are trying to get box diamond on one side and box diamond on the other. That means what we need to do is add boxes on both the antecedent and consequent, which we can do using derived rule 1. So box diamond, P implies box diamond, P, derived rule 1 applied to line 6. And then we have our propositional logic, which says that if box diamond P implies box diamond P, and box diamond P implies box diamond P, then we can take these two conditionals together and turn them into an equivalence. So propositional logic applied to lines 7 and 3. So a slightly messy proof, but if you want a clean copy, you can write up your own clean copy. And in exactly the same way that we were able to prove 2 from 1, you can prove 4 from 3. So I'll leave that again as an exercise. So this gives us proofs of 4 modal reduction principles. They make life so much easier in doing proofs in S4. Anytime that you see 2 boxes or 2 diamonds, you can always reduce down to just 1. Anytime that you've got flip-flopping of the operators, so box, diamond, or diamond, box, you can reduce that to just 1 set of alternating operators. Of course, the interesting question is, can we prove any other reduction principles? And that is what we will talk about next time. So join me then for the answer to that question. Until then, take care.